Hey everyone, welcome back to Stat and Research 2 or Stat 5616. I hope you guys had a great weekend. For this week, we're going to be focused on completely randomized designs. The structure of this week is you're going to have 4 videos. The first one, this one obviously, is going to be focused on ANOVA and how to do the analysis of a completely randomized design. The second one will be talking about contrasts. The third video will be talking about multiple comparisons. These two are post ANOVA analysis types. And then the fourth one will be talking about power and sample size calculation. Then you will have a homework number 2 is due on Friday by midnight on Canvas. So let's get started on talking about completely randomized designs. In this lesson, we're going to give an introduction to completely randomized designs, or CRDs. We'll introduce model and notation for completely random designs, the analysis of variance table, which should be reviewed from Stat 5615, and then some theory about ANOVA along with an example. The example that we're going to be focused on today is going to be the highway paint example. And the goal of this example is to compare the reflectivity measurements of 3 new paints to the paint currently used on the highway. So we have 16 similar highway sections, and we're going to randomly apply the paint to 4 sections. Okay, our response is going to be the percent decrease in reflectivity. So we have 1 treatment factor paint, and we have 4 levels. The current one, and then the 3 ones that we want to compare to. Each treatment factor is going to have n replicates. Those are the sections of highway per treatment. So therefore, our total number of EUs, or experimental units, is going to be a capital N, which is equal to 4 times 4, number of replicates times the number of treatments, which is 16. And in this box right here, we can see all of the responses from the percent decrease in reflectivity. And then in this column right here, we can see the group means. Now, a question that we're going to want to ask is there a difference across these paints in terms of reflectivity? And if we were looking at this, they all seem pretty close, but it's not only important to look at the mean, but it's even more important to look at the variance within the treatments and between the treatments. And so that's where our analysis for ANOVA is going to come from. But before we get there, let's talk about completely randomized designs and their characteristics and some of the parameters associated with it. So first, a completely random design is going to be our easiest design up for this class. And then throughout the class, we're going to build and build and build. And so to start off super easy, our CRDs only have 1 treatment factor. In this case, it's paint. In other cases, it could be combined treatment factors. So in lesson 2, I'll show an example of that. There are also no blocking factors, and you only have to do a single randomization. Our parameter and notation is we have little t number of treatments, and we have little n I, where I is going to represent the number of treatments. Our total number of EUs is going to be the total number of replicates from each treatment. Now, in our case up here with the highway paint, we have a balanced design because we have equal number of replications per treatment. And so when that happens, all of the NIs are going to just be equal to a simple small n. And our number of EUs is going to be equal to n times t. So it's important, before we go straight to the ANOVA, it's always important to understand what our statistical model is, because understanding the model is going to help us to understand the analysis and the interpretations. And so again, we're going to start with the simplest model, and then over the next couple of weeks, we're going to build and build by adding more blocks and more treatments. And so something that you probably saw in Stat 5615 was this model, where we have Y, I, J's, which are going to represent our response. So in the highway example, that's the percent decrease in reflectivity is going to be equal to mu I plus epsilon I j, where mu I is going to be our mean response under treatment I. Again, here's an important thing that we're looking at is that we're allowing the means for each treatment to differ. And then we have an error term. This error term is basically saying that there's background noise that we can't explain because we can't explain everything. And so we're using this to help represent that stuff we can't really put into our systematic variance. Okay, we also need this error term so that we have a statistical model. If the error term wasn't there, then this would be a deterministic model. We're also making an assumption that it's normally distributed, centered at 0, and has some variance, which we'll denote by sigma squared E. Okay, now this is what we're going to call a means model, but we can decompose this model to actually represent the grand mean, so the overall mean of all the observations, plus some treatment effect. And this model is actually known as the effects model. And so what the effects model will look like is Yij equal mu, the grand mean, plus the effect due to treatment I, and then plus our error term. Okay, and so to help understand this a little bit better, I have this conceptual model right here. So let's just talk about this real quick. So we're gonna have a true mean, the mean for all of the observations, and that's represented right here. This is the grand mean. And then for each treatment, in this case we have 3, we are also going to have our group means. So this purple dot right here is the group mean for treatment 1. Here's the group mean for treatment 2. Here's the group mean for treatment 3. Okay? And again, for this conceptual idea, we are using the population parameters, which we will have to estimate using our data down the road. So for each treatment, we'll have a group mean, and then we have observations. So these black triangles represent our observed responses. Okay, that would be in our pain example, these various numbers. This right here would then represent the purple dot if we were looking at actual data. It doesn't matter if we use the means model or the effects model in the analysis, you're going to get the same answer. But using the effects model, the effects model might help us to understand this. And so why I like the effects model is because we can look at these alphas. So the alpha for treatment 1 is represented by the difference between the group mean minus the grand or overall mean. Again, here's the alpha 2 and here's the alpha 3. And it's easy to look at if these alphas are very big, then that means that these groups are far away from the overall mean, which implies that the treatment effects do differ. But if these alphas are really small, then these groups are going to look closer and closer to the grand overall mean, and so that would imply that the treatments really don't have an effect. There's also another, so let's go back to that assumption we were making right here with the error terms that we say are normally distributed. So we can say here that the data is also normally distributed, where we're going to be centering around the treatment group mean, and we're going to have some variability. We could either represent that as the standard deviation, or we could represent that as the variance. All this assumption's telling us that our data is normally distributed, where the random error term, which is the epsilon, is on average 0. So what that's saying is that if we took our observation or our observed, the triangle, minus the mu, and we looked at all these, on average, they're going to be 0. So we're going to be centering around our normal, and then we're going to have some type of spread. Okay, so one more time, all this normal assumption saying is that the majority of our mass under our distribution, think about the empirical rule, is going to be focused around the mean, and then there's going to be some decay from there. Okay. Also, this difference between the observed and the overall group mean is will be called our residual error. So we just talked about random variability, that is, our error terms are random, which is also going to make our data random as well. What I mean by that, in the simplest of terms, is our data is random. That is, if we did an experiment again, if we were to rerun this highway paint example, we wouldn't expect that all of our data would be the same. And so if our data is random, then the distance from our data to the overall mean, this error, is also going to be random. So a random variable, again, is any variable whose value changes from experiment to experiment. So again, if we did that highway example and we reran it, we wouldn't expect to get the exact same reflectivity measurements. So the reflectivity, or the response y, is a random variable, as well as our errors. Okay? What is not random are our mu i's, our mu, and our alpha i's. Those are fixed parameters from the population, and our goal is to estimate these values, which we'll talk about in a moment. And once we estimate these, they will become random, and I'll show you why in a second. Okay, so with a random variable, you can also understand what to expect with that random variable. Okay, and this is going to be the expectation. And all the expectation is that if we were to continually repeat the sample and repeat and repeat and repeat over and over again, we would expect to find on average. So for instance, in the highway example, if we could continually repeat applying paint and finding the response, we would hopefully expect that we would get the group mean or the true population parameter. For our error term, if we were to, again, for our error term, the expected value on average is going to be 0. And so that's what that's saying. So if we were to repeat it and we were to look at the difference between the group mean and the observation and continue to do that, we would expect that the expected value of our errors is 0. Another thing that we'll talk about is unbiased estimators, and it's just an estimate whose expectation is equal to the parameter being estimated. So if you've had any previous stat courses, you may have looked at the expectation of the mean. So what I mean by here is the expectation of y bar, which is mu. And so y bar is an unbiased estimator of mu. Okay. Do I expect for all this to click right away? Absolutely not. We're going to be continually talking about random variables, expectation, and unbiased estimators kind of throughout this class a little bit. Okay, it's just to introducing this because there is a little bit of theory that I do want to talk about towards the end. But before we can do that, we need to understand how to estimate our parameters. Because again, we had parameters mu I, mu, and alpha, which are not random variables, and these are the population parameters. So we need to estimate them using our data. In order to do that, I want to introduce some notation, which I think should have been introduced in Stat 5615, but if it wasn't, I want to just introduce it here. And so this is called the dot bar notation, where it's going to average over the missing subscript. So let's be a little bit more specific. So the dot is going to imply summing, and the bar, that's not a minus sign, that's going to be a bar. Pretend there's some variable, we'll make it smiley face variable, implies average. So let's say we have 3 treatments with n replicates, okay? And so group 1 will have y11, y12, y13. Group 2 will have observations y21, y22, and y23. And group 3 will have y31, y32, and y33. Okay, and now if we were to look and find y1 dot, this would be equal to y11 plus y12 plus y13. Now, if we added a bar such as that, we're going to take the average. Okay, so let's go one more example. Y2 bar is going to represent y21 plus y22 plus y23 divided by 3. Another important one that we'll see is the y dot dot bar, which can look like y1 dot bar plus y2 dot bar plus y3 dot bar divided by 3, or a little bit more drawn out is y11 plus y21 plus dot 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 y33 divided by 9. So we're taking the average of all of these. Okay, where this is going to come into play is now our parameter estimation. So recall we have parameters in our model, either the means model or the effects model, and we want to estimate these parameters. How we do that is by, if our mu parameter is estimated by the grand mean, so taking the average of everything, our treatment mean is mu I equal to mu plus alpha. How we represent that, mu I is equal to yi dot, so whatever the treatment is, it's the treatment mean. Then we have our effect treatment alpha, which is going to be the difference between the treatment mean and the overall mean. In statistics, we put hats, which are right here, on parameters that we're estimating. So here's our parameter. We know it's an estimate because of the hat. All these estimates are unbiased estimates. Now, previously we were looking at the conceptual model, and now I want to kind of re-show you guys how the estimated model and thought process works. And so we have our estimate for the overall mean with this blue line. Then we have our estimated group mean, and then we have our estimate for alpha I. So the difference between the group mean minus the overall. So hopefully you noticed that with this estimated model, there's a big connection between the estimated and the conceptual model. And I'll leave that for you guys to make those connections between the estimated and the conceptual. How this can relate back to our pain example is we had our means and then we had our observations. So for our pain example, we can visualize this in R or jump. I have both depending on which method you're using, where the red dots here are the mean, the blue are the observations. In R, I drew the overall mean, so this is mu hat, that dash line. We could have done it in jump, I just didn't think about it when I made the jump plot, okay? So now that we have some notation, we have some understanding of what's being seen in the estimated model. Our goal now and our objective of completely randomized designs is to test whether there's a difference in the treatment means, or there's just a difference in the treatments. And there's two ways that we can write our hypotheses for these. So if we were using the means model, i.e. the yi equal mu I plus epsilon I j, then our hypotheses would be our h naught is mu1 is equal to mu2 is equal to dot 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 equal to mu t, versus the alternative, which is mu I is not equal to mu j for some I not equal to j. So at least one of these groups is going to differ. Now, if we were using the effects model, yij equal to the overall plus the treatment effect plus our error, then our hypothesis would look something like this. Alpha 1 equal to alpha 2 dot 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 is going to equal to alpha t is going to equal to 0. Again, the 0 comes back into play when we're looking at these. If they're big, they're going to look very different. But if all these are looking like 0, there's going to be no difference between these treatment groups. Let's get our alternative versus H, which is going to say that alpha I doesn't equal 0 for some I. Okay? Now that we got our hypothesis, our next goal is to perform our ANOVA. So, and again, with ANOVA, our goal is to see if the group means are different from each other compared to the within group variability. Again, ANOVA is all about looking at the variability. While it's great to look at the means, really where things start to differ is in their variance. And so if we remember back to lesson 1, I was talking about how one of our goals is to measure all the variability and then break it up into systematic variability and random variability. And so we do that in ANOVA. And how we do that is by first, we look at the between treatment sums of squares. And so this is going to measure the variability due to our treatment effect. Okay? This is the group to group variability. And so this is going to be looking at our differences between our alpha. So boom and boom. Okay, we're looking at the differences between the groups. And we're trying to see if there's an actual signal here. So I wrote out the notation. You can see that we're squaring our alpha i's. Alpha i's are our treatment effects are playing an important role of between treatment sums of squares. That's where our variability due to treatment effects coming in. The other variability we want to measure, we call it error sums of squares, sums of squared error. is going to be the within group, or the distance between each observation and the group mean. So what I'm talking about here, the sums of squared error in a completely randomized design, is looking at the within. So how much error is happening here? So sums of squares treatment is looking at the difference between here. The sums of squared error is looking at the variability within the group. Okay? And then the total sums of squares just measures the variability from all the sources. So this is additive. This is an additive property. Once we have a way to measure the variability within our experiment, we now want to start to look at our test statistics. And our test statistic is going to be looking at the signal to noise ratio. So we have our sums of squares treatments divided by our degrees of freedom, which is t minus 1, divided by our sums of squared error, divided by, and this should be a little t. Oops, little t. Okay. Another way of saying this is we're going to look at our mean squared of our treatment divided by our mean squared for our errors. So it turns out if you take this signal, our signal is kind of what we're seeing from our treatment, divided by our noise ratio, it's going to follow an F distribution, okay? With degrees of freedom, oh, I didn't write that. So this is going to follow F distribution with degrees of freedom 1 equaling t minus 1 and degrees of freedom 2 equaling n minus t. And similar to hypothesis testing that we learned, or that you guys learned about in Stat 5615, is that we're going to reject the null and conclude that there is a treatment effect if our F statistic that we observed is greater than our F of given a certain significance level and degrees of freedom. Okay, this point right here has become more, what's the proper word? Unuseful, maybe, as technology has gotten better and better, because this involves using an F table. And since we have software like JUMP and R, we typically don't look at this, and we more look at the p-value. Okay, but it's always good because this helps helps us get an idea. So how this plays into looking at the p-value and the F is you're going to get this one-way ANOVA table. And it is important, star important, to understand this table and how the elements work together. So first, our degrees of freedom for our treatment plus our degrees of freedom for our error is going to equal our total degrees of freedom. So this is additive. Our sums of squared treatment and error, again, this is additive to get you this. Our mean squared treatment, our MST, is going to be equal to SST over t minus 1. So it's this column divided by this column. Our mean squared error is going to be our sums of squared divided by our degrees of freedom. And then our test statistic, or our signal to noise ratio, typically known as I write it as F observed just because that's what we observed using our data, is the ratio between our mean squared treatment and our MSE. So it's these two divided to get here. It's important you know this for multiple reasons on tests. If I show you this, if I give you some of these, you should be able to figure out the rest. What's really important, and then kind of what's going to lead to the next portion of notes, is our F statistic, again, which I typically write as F observed, is going to provide us with statistical evidence in terms of our hypotheses. So if our F observed is big, F observed is big, then we're going to oftentimes reject our null hypothesis and say that at least one of these groups is different. And so the treatment is going to have an impact. Now, is it big enough? I'm going to put big in quotes because it's got to be big enough. And what I mean by that is let's go to our next page of notes and get some further insight into what I'm trying to tell you guys. So, and this is also why I brought in expectation and random variable, is to help us understand this F statistic. So again, our F statistic, our F observed is going to be MST over MSE. And so we're going to focus on telling you why we look for big F stats, just to give you some intuition on why. So we have MST, and if we recall, MST is derived by looking at our Y I's and our Y bars. Okay, remember, these are random, so when we take an expectation, we're going to get this. What does this mean? What this means is our MST is composed of variability from our groups plus variability of some proportion of the background noise. Okay. Our expected value for MSE, again, those have components of our observations and the means of our observations, is going to be our background noise. Okay. Well, the expectation of MSE is our background noise. This is also an unbiased estimate. Okay. Now, if we think of our null hypothesis for ANOVA, which again, alpha 1 is equal to ... equal to alpha t is equal to 0. So if we are under the null and we assume the null is true, then that means that this error, or not this error, this term is essentially 0, which is going to apply that our MST and our MSE are equal, and so that our F will be 1, roughly. Okay? But if our null hypothesis isn't true, and we're working under the alternative, that's assuming that this term will be positive. Why? Because we're squaring it. And so we're adding more to our background noise. So our treatment, if this is getting better, our treatment is having an effect, and it's more than just that background noise. So this is going to get bigger, and so we're going to have a big F. The question here is what's big enough? And that's where our p-value is going to come into play, and this is going to help us figure out what is big. I just wanted to kind of give you guys this as some intuition on why we're looking at our F statistic, why we want big Fs, and kind of all that. So now that we've briefly recovered ANOVA and completely randomized designs, let's do a concrete example to help us get our brains around this concept. So we're going to go back to our highway paint example, where again, we want to compare and see if there's a difference between the new paints and the current one. So we have 4 treatments with 4 replicates. Okay. We have our group means, so this would be Y1 dot bar here, Y2, Y3, and Y4 dot bar. Our grand mean is going to be 25. And so our first step is to create our hypotheses tests, or not create them, but write them down so we understand what we're doing. All 3 of these are valid hypotheses. This one is under the means, this one is under the effects model, and this one's just using straight words. Okay? Now, our next step is to compute the test statistic. And so, boom. So here, I wrote out all the formulas. A lot of times people want to see this so they can get an idea of what's happening. Note, I'm going to make this a note. You will not have to compute these by hand on homework or test. In this class, it will be perfectly fine for you just to understand where SST is coming from, where TSS and SSE is coming from, i.e. those conceptual models, those estimated models we were talking about. I'm not going to have you write it by hand because we have computers, and let's use technology to our advantage in this case. So we have now our test statistic in which we got 0.98. How we got that was we computed our SST, we computed our SSE using the additive property. We've got our degrees of freedoms. We calculated our MST, our MSE, and to get our F observed statistic. Now, one way you can make a decision about this is through rejection region. And what we can see right here is that we have an F observed of 0.98. And if we go back to our further insights that we were just talking about, we can probably almost surely predict that we are going to fail to reject our null because our F observed is less than 1. But let's just go through the rejection region and how to do it on a computer based on using F tables. Again, F tables are very, very old school, but they'll help us to get an idea. And so if we were to draw a picture, maybe not my best, this would be our F distribution with 3 degrees of freedom for the numerator and 12. And so if the null, so under the null, we would assume this distribution, and we would make a cutoff point such that the area under this curve is 0.05. And this is going to represent our significance alpha. Now I notice we just introduced alpha i's, and now we have an alpha that represents our significance level. They're not the same alphas, just want to make that clear, okay? And so we have this cutoff, which we found to be 3.94. Again, this is calculated using F tables. You could also calculate this using software. But if you're going to use software, just use the p-value. Then what we would see is we'd look at where our F observed would be. And in our case, roughly, our F observed would be here. And so our F observed value is not in the rejection region. And so thus, decision should be fail to reject. Oh, I see what it is. Don't worry about that. Your decision, you will reject H naught if your F observed is greater than this. Since it's not, we fail to reject H naught and conclude that there is no reason to believe that the paint have different percentage decrease in reflectivity. Now again, this is pretty old school using tables and rejection regions, and in practice, we typically use computer output to generate p-values. So in JUMP, you would see this, and in R, you would see this result. To get these results, go watch the video that I have posted for JUMP and R. What we want to look at is to see where the p-value is. P-value. And so conclusion is that since the p-value is greater again, our p-value is 0.4333, is greater than 0.05, we fail to reject H0 and conclude that there is no reason to believe the paint has different percentage decrease in reflexivity. So to summarize this lesson with ANOVA, let's just flip this over. So quick summary for performing the analysis is we have to write our hypotheses. Then we are going to compute our F statistic / p-value. And then we're going to make a conclusion. Where if the p-value is less than or equal to alpha, we reject H0, and if the p-value is greater than alpha, we fail to reject H0. Now again, I'm not saying accept H0 or the null. I'm just saying there's not enough evidence to conclude that the alternative.